Okay, so we're back now with our third video in these notes for finding inverses algebraically. In example 1, we looked at the inverses of linear and cubic functions. In example 2, we looked at the inverses of radical functions. And so now in example 3, we're going to take a look at finding the inverse equation of some rational functions. Okay, so up at the top here, it reminds us to first identify the range of this function because it's going to become the domain of the restriction on the inverse, similar to what we did in the square root functions on example 2. So when I take a look at my graph of my f of x 2 over the quantity x minus 2. Remember that h of 2 moves the graph to the right 2 units, so that's why my vertical asymptote is now translated over to x equals 2. And then the domain of that rational function would be negative infinity to 2, non-inclusive union 2 to infinity, all real numbers except 2. Okay, the range, though, is not affected by that horizontal translation because there was no vertical shift. My k is 0. The range is only excluding this horizontal asymptote here at 0. So the range of my original function is negative infinity to 0, non-inclusive union, and then 0 to positive infinity, right? That is all real numbers except 0 because of this horizontal asymptote here along the x-axis. Okay, so that range of my original function f of x will become the domain restriction on the inverse. So my inverse will be restricted to exclude 0 from its domain. Okay, so now I can go ahead and find the equation of my inverse by substituting y in place of my function notation. So I'll have y over, or y equals 2 over the quantity x minus 2. And then my next step is to reverse or switch the positions of the x and the y. So now I'll have x equals 2 divided by the quantity y minus 2. Okay, and then I want to solve for y. Okay, so to do that, I'm going to remember that this is a proportion, so I could put this x over 1, and then I can cross multiply to solve that proportion. So on this side, I'll have x times the quantity y minus 2, right? That's multiplying this diagonal. That's equal to the other side, 2 times 1, which is 2, right? And that was by cross multiplying. Now I want to try to get my y by itself, so I'm going to divide both sides now by x so that those x's cancel, and then I'll have y minus 2 is equal to 2 divided by x. And then to get y by itself, I'll add 2 to both sides, and y is equal to 2 over x plus 2. Okay, so my last step then is to replace the y with my f inverse notation. So f inverse of x is equal to 2 over x plus 2 with a domain of all real numbers except for 0. Okay, so go ahead and pause the video and try example B on your own. And for example B, I'll just give you a hint. Up here it says be alert for problems requiring regrouping and factoring out a greatest common factor. Okay, so that's likely to come up here in example B. So as you're trying that one on your own, keep that in mind. And then when you're ready, go ahead and resume the video and we'll go over this example together. Okay, so back to example B, I'm going to look at the graph of f of x and identify its range. So the range, since I have a horizontal asymptote here at y equals 1, that's going to be excluded from my range. So negative infinity to 1 union and then 1 to infinity, where the 1 is non-inclusive. Okay, that range of f of x will be the restriction on my domain of the inverse. So negative infinity to 1 union 1 to infinity will be the restricted domain. Okay, then to find the equation of that inverse, I'm going to replace the inverse notation with y equals. Let me get my white out because I just made a plus there. There we go. So y equals x minus 1 in the numerator and then x plus 1 in the denominator. Okay, now when I go to switch my x and y here, I have to remember that I'm doing that with all of the x's. So since this rational function has an x in 2 places, they both become y's. So I'll have x now equal to y minus 1 in the numerator and a y plus 1 in the denominator. Okay, now I want to solve for y, and just like I did in example A, I'm going to cross multiply to solve this proportion, and so this direction I'll have an x times the quantity y plus 1, and then multiplying 1 times y minus 1 is just a y minus 1. Okay, now I'm going to distribute to get rid of those parentheses. So distributing this x over the parentheses gives me an xy plus x is equal to y minus 1. And my goal here is to get y by itself. And right now I have 2 y's. So to make this a little easier on myself, I'm going to get the y's together on the same side. So I'm going to subtract y from both sides. And then I'm going to also, while I'm at it, subtract the x from both sides so that I can move the x out of the way and get my y's together on the same side. So that's going to leave me with an xy minus y equal to negative x minus 1. Okay, now I want to notice that this xy minus y, that binomial, has a greatest common factor of y. So I'm going to factor out that y to the front, and I'll have y times the quantity x minus 1 is equal to negative x minus 1. And then I can see that if I divide both sides by this binomial, I'll have my y by itself. So I'm going to divide both sides by the quantity x minus 1. And so here these x minus 1's cancel and my y is by itself. It's equal to the other side, so I can swap out my y now with the inverse notation, f inverse of x, and that's equal to negative x minus 1 divided by the quantity x minus 1. And that's the equation of my inverse with this restriction on the domain, where my domain is all real numbers except for positive 1. So now if we turn over to the back, example 4 asks us, why do we not look for the equation of the inverse for a quadratic or an absolute value function? Okay, we looked at the equation of an inverse for linear, for cubic, cube root, square root, and rational functions, but none of the examples in our booklet asked us to find an inverse for a quadratic or absolute value. And if we think about why that would be, the parent graph of the quadratic function is a parabola, right? The parent graph of the absolute value function is a V shape, and both of these fail the horizontal line test. Okay, and if you recall, in our first step on the front, we were instructed to use that horizontal line test to determine if the function has an inverse function. Since the quadratic and the absolute value fail that horizontal line test, they are not one-to-one. So they're not going to have an inverse that is also a function. Okay, so they fail the horizontal line test. So not one-to-one, which means no inverse is possible, right? We'd be able to make a graph if we reflected over the line y equals x. We could make a graph of that reflection, but we wouldn't be able to write an equation for the inverse because it's not one-to-one. Okay, what other functions will not have an inverse? From our parent graph foldable, that would be the constant, because that's a horizontal line. It by default fails the horizontal line test. And then we also looked at the ceiling and at the floor functions, and those, because they're made up of little horizontal line segments, would also fail the horizontal line test. So absolute value, the quadratic, right, and the quadratic, and then the constant, the ceiling, and the floor functions. Those would be from our parent graphs foldable functions that we will not look for equations for their inverses because they are not one-to-one.